Pedro said, I will be telling you about dark matter. The visit so far has been amazing, and thanks to the organizer, of course. So I will also be giving 4 lectures, and this is roughly the plan for the 4 lectures. First, today, I will be showing you some slides, which are mostly just pictures, about what evidence we have for dark matter. So most of the discussion will still be on the board, but I don't want to be drawing all of these nice pictures that people have taken with astrophysics or cosmology instruments. So you will see the pictures as they are. So after today, I will go into more model building or more analytical things where we'll talk about 2 leading dark matter candidates. The first one is WIMP, or weakly interacting massive particles. So how many people have heard about WIMPs? Oh, okay, a lot, great. Okay, so then we'll be talking about axions, which is another leading dark matter candidate. How many axions? Oh, also a lot, great. Okay, so these are the 2 examples we'll cover. Try to see how, why they are motivated and how they produce in the early universe and then evolve afterwards. So in the last lecture, which might be more than 1 lecture, I'll be telling you about another aspect of my life, which is putting on an experimentalist hat and try to see how we can design experiments to look for these dark matter candidates with all kinds of different instruments, technologies coming from optics, AMO, condensed matter, and how they can all be used to look for something that we don't know, that is dark matter. So this is roughly the plan. And to start with, like Ricardo did yesterday, I will be telling you a few things about numbers and units, okay? So throughout the lectures and also for your exam, so now you should be high alert, we'll be using the number system where pi is equal to 3, equal to 4, equal to 1. Okay? Which means all the answers that we'll be talking, all the things we'll be talking about, and all the answers you are supposed to be getting is only qualitative. You only need to get things which are correct up to a factor of 10, or and then get to the qualitative feature right. It is not very important to get all the number to be very, very precise because we don't even know if these things exist in the universe or not, right? Okay, so far so good? Okay, so the one number that we'll be using, which is not equal to 1, is the fine structure constant. And in our unit system, this is, in reality, it's 1 over 137, otherwise known as 10 to the minus 2, okay? So we'll be trying to track some of the scalings with this number and see how different interactions depends on the coupling constant differently, okay? So that's basically number 1. So here are how we treat numbers. Every time you see a pi or 2, you can drop them. The second thing that we are going to do with numbers is we are going to choose a unit system. So here we'll be choosing a unit system called natural units, where a lot of other things are set to be 1. Okay? So this is the unit system that we'll be using. The Planck constant, h bar, the speed of light, c, and the Boltzmann constant, kb, is all chosen to be 1. And what this does is, as you saw already yesterday a little bit, is it gives you a relationship between different units. Okay? So let's start with 1. The first example, let's say c equal to 1, right? Well, we know in reality it's equal to 3 times 10 to the 8 meter per second, right? So what this means is I'm saying that 1 meter is equal to 3 times 10 to the minus 9 second. Okay? So by choosing this unit where c equal to 1, I'm setting a relationship between the length unit and the time unit. And we are going to be treating them the same way. Right? So I get length equal to time. So in the future, I will be talking about something which is 1 light second long or 1 second long, right? Or 1 light year long or 1 year long. So, the reason I'm able to do that is I'm choosing this equal to 1 unit, and which relates meter per second. Okay, good? So what other things does it do when I choose c equal to 1? Any guesses? Great, okay. So Einstein told us this, right? E equals mc squared. So c equal to 1, which means energy and mass are the same thing. In particular, not only that, like energy, momentum, right? Mass is all the same unit, right? So now the mass unit, the one that you're mostly familiar with, is gram, right? So now like this unit is also related to momentum and also to energy. So energy, the unit that we'll be using is called EV, electron volt. So a proton is roughly 1 GeV, or 10 to the 9 electron volt. The electron is roughly 10 to the 6 electron volt. So the reason we say they're like a mass is like a GeV is because I'm choosing this unit where c equal to 1, so energy and mass are the same thing. Okay? So with these choices, basically the unit I'm left with is EV, which will be all the mass units, energy, momentum, mass, right? And then I will be using meter or second when I talk about length or time. Okay? But they are the same. All right, so this is the simple example. The second one is h bar equal to 1, okay? So what does h bar equal to 1 do? You know? Where is the first time we saw h bar in physics? Huh? What's the relationship that, what does h bar measure? Yes, angular momentum, great. So this is what we learned from Bohr, right? The angular momentum of atom is, like energy levels, is separated by h bar, right? So here, and this is basically the mass times the velocity times the distance is equal to h bar or equal to 1, right? So I already know that the velocity is the same unit as c, so velocity has no unit. So let's just drop it. So now like what happens is it is relating a mass unit and a length unit, right? So if you remember from yesterday, h bar is equal to 200 MeV times a Fermi, right? So now by choosing h bar equal to 1, what I'm doing is I'm setting 200 MeV and inverse Fermi to be the same thing. Okay? So now the length unit is gone, and in the future I will be talking about length units like 1 over EV, EV inverse. How long is that? Do people know? It's roughly a micron, okay? So EV inverse now becomes a length unit, and it's roughly equal to 1 over micron. Okay? So yeah, with this, I'm setting mass unit to be 1 over length. Okay? So the third thing that we'll be doing is without 1 over, right? Micro. Yeah, sorry. Yeah. I don't do inverse on both sides. Yes, thank you. Okay. So the third thing that we'll be setting to 1 is the Boltzmann constant, right? Kb equal to 1. So where does this show up? Which class did you learn this? Statistical mechanics, right? So it relates energy with temperature, right? So when I set this equal to 1, right, what I'm doing is I'm setting the energy unit and the temperature unit to be the same. So now, instead of talking about Kelvin as a temperature unit, I can also talk about Kelvin as an energy unit, right? So, but like more often, like I'm really using EV to tell you like what's the temperature of the system. So here you will also need like a relation, and what you get is roughly like EV is equal to 10 to the 4 Kelvin. Okay, so as you can see, EV is very hot for a lot of practical purposes. Okay, so what I achieved with these, like 1, 2, 3, or ABC, with these 3 choices, is I reduce all the units that I have, for everything that we know about physics, to 1. Okay, so there's only 1 unit. That's EV.
You won't do G equals 4 because
yeah, I'm getting there.
Okay, you relate mass to length, so G does the same.
Good. Yes. Just wait a little bit. Okay, I'm getting there. So, but like the main thing that I will be using are these 3, such that now EV is a unit which I use for everything. Okay, energy, length, momentum, mass, temperature, whatever. Like electric field, magnetic field, you can convert all of these things to EV or EV squared or EV to some power. And I wrote some homework that you can work out to see like if you get all the units like relations right. Okay? So this is the unit system that we'll use. And as one of the students anticipated, there's also like another thing that I can set to be 1. And it's also a fundamental constant. And that constant is G Newton. So in principle, I can also set G Newton equal to 1. So G Newton, as Ricardo said yesterday, is a unit which relates length over mass, right? So this is how G Newton is defined. So Gm equal to a length scale. So famously, he told you that if I have a solar mass, the length scale is 1 kilometer, right? So if I could, again, set this to be equal to 1, right? Then basically, the mass is equal to length. It's also equal to 1 over length, meaning length has no unit and the mass has no unit, right? So if I do this choice, then basically I remove the last units from the system, and everything now becomes dimensionless. There's no units, and all the energy is measured in Planck units. So if I say something is 1 GeV, now this mass would be, so in this, if I set G equal to 1, then a GeV is equal to GeV over m Planck, that is 10 to the minus 19. So a proton in this unit is 10 to the minus 19 mass. Okay, so it's getting more and more confusing. So we are not going to do it, but there does exist a number which is of fundamental importance when I choose this G equal to 1 unit. Okay, and that is the energy density of the universe. So if you remember from yesterday, the energy density of the universe is 10 to the minus 23 gram per meter cubed, right? Hopefully I copy it down correctly from Ricardo. So if I did, then like you can take this number and try to put it in first EV unit, and then try to put it in a unit where G equal to 1. Okay, so you can do both of those. And if you do it for the unit where G equal to 1, then the number you are going to get is 10 to the minus 120. So it's a tiny, tiny number, which is the energy density of the universe today in Planck unit. Okay, and this 10 to the minus 120 number is actually a very important number, and we actually don't understand why it is so small. And the fact that we don't understand it is called the cosmological constant problem, where basically in this language, is we don't understand why the energy density in the universe is so much smaller than Planck energy density, and why the universe is so big. And that is basically related to this number. When you go to graduate school, probably someone will tell you about the cosmological constant problem, and why it is a very weird thing that this rho in Planck unit is so small. Okay? Any more questions about units? Good. Okay, so like we'll be practicing units throughout, and the important thing that you get from these practices is that you realize when to use a length unit and when to use a mass unit, and how mass and length are related to each other. And we'll see how these things work when we play with this unit system in the future. Okay? All right. So now let's come back to the real thing. So now it's not working. Let's see. Okay, maybe it's coming. Yeah, so it's coming back. So as it is coming back, maybe let me ask you guys, like, what do we know about dark matter? What are the evidence we know that they exist? Anyone?
Collision of galaxies.
Huh?
Galaxy collision.
Galaxy collisions. Oh, okay. That's the first one. Okay. Huh? Bullet cluster. Okay. Wow. Okay, that's not where I think like this will start. Where the first evidence we have for dark matter is actually rotation curves, right? And then CMB, and then bullet cluster. But since you guys choose bullet cluster to start with, and I did too, we'll start with bullet cluster. Okay. And to me, like it's the measurement that really tells us that dark matter exists. Okay, so this is a picture of a bullet cluster, right? So, what this picture is describing is the following. So I have two galaxies, Galaxy 1 and Galaxy 2, and they have collided with each other. So, so in principle, if they don't interact with each other, then as time evolves, I'm going to get to the point where Galaxy 2 is on the left and Galaxy 1 is on the right. Okay, so and like this picture is taking a snapshot of this evolution at this very moment. Okay, so of course this is not what we see, and the reason is that the galaxy actually interacts with each other, right? So so in the case where they don't interact, this is what we get, and in the case where they interact. Let's say I have two pedals and I throw them into each other. What happens? They smash and they are in the middle. Okay. So so this is possibility 1, right? Possibility A, and the second possibility is I smash two things into each other, and they stuck in the middle. So this this is 1. Actually, this is 1 and this is 2. Okay, right? But like because they are merged into each other, like I can really not distinguish like which one is which. But the important thing is that there is something in the middle instead of on the two sides, right? So this is a possibility B. So this is what happens so this case is what happens for stars. So as you can see, like from the picture, there are stars on the left and on the right, because the stars, they are very, very dilute. And when the galaxies interact with each other, they just go through the galaxy. So they don't interact, and they basically end up where they would have been, as if like the other one doesn't exist. Okay, so stars are here, right? Is of course here. The second thing is that that exist in the galaxy are gases, right? So these are ionized gases of protons, ions, and also electrons. So when they collide into each other, they really interact with each other because they interact like electromagnetism. Electromagnetism is very strong. It can hold this board on here, right? And I can hold this chalk, right? It's all electromagnetism that is doing the job. It is so much stronger than gravity. So when two things which are charged get into each other, they get smashed into each other, and they get in the middle. Okay? So these are where the gases are. Okay? So, in this picture, it is basically shown by the red color in the middle. So there is a third component which on this picture, which are these blue-colored regions. And that is a measurement of where the gravitational potential is in this picture. So let me first tell you the conclusion. The conclusion is that when we do some measurement, and the measurement is called gravitational lensing, what we discovered is that the gravitating matter is not in the middle, like where the gases are, but like it's more close to where the stars are. And with the measurement, you can also like even measure like how much gravitating matter is in these regions. And you found that the amount of matter you have in these regions is much more than like the stars themselves. And these gravitating matter is what we know as dark matter. Sorry. I don't know how to make it not stop. But anyway, okay. So that is, so the blue is where the gravitational potential is, and which is where the matter is. And the matter is much more than the visible matter, which implies there are dark matter. Okay? So, so this is the conclusion, but I will also be telling you what is gravitational lensing. Okay? Good with conclusion? Okay. So, lensing. So, of course, like I assume like everybody has seen like lensing in optics. So the idea is if I put a candle here, right, and I have a lens right in front, then the candle is going to emit light. Let me make it a little bit bigger. And eventually, sorry, not like this. Okay, let me see what's going on. Right, sorry. Yeah, so let's say like this is the focal point. Then they go back, and this one go back, and I have a bigger image, right? Okay, so this is basically lensing. If I have an image, some object in front, behind the lens, I'm an observer here, and I see a magnified image of this object because there are lenses which bend light rays. Okay, so the same is true for gravitational lensing. So here, instead of lens doing the job of changing the direction of light rays, what happens is I have a star, which is emitting light like the candle, and I have some gravitational potential in the middle, and we are here, and the gravitational potential, the gravity bends everything, including light, so these light rays will do curves like this, and from the perspective of the observers like us, then we see either a magnified image, we can see multiple images, and that's what's called strong lensing, or like we can just see some like an image which is brighter than usual. Okay, so from the measurement of these background stars, behind the gravitational potential, or behind like this cluster, like this galaxy collision, which is this part here, we can know from the properties of the star behind it what is the gravitational potential in the middle and how much mass is in the middle. Right? So that's the idea of gravitational lensing, and with this, we measure that there are a lot more gravitating matter in this picture than what the stars were showing us, and that's how we know that dark matter exists. Good. So, qualitatively, we learn something from this picture, and let's say like what we learned, right? So for the first one, like I will be summarizing. I will summarize it for you. So there are a couple things that we learned. The first one is dark matter, they do interact, and they do interact gravitationally. Right? The fact that they provide a gravitational lens for the stars behind a star and a starlight behind it tells you that they do interact gravitationally. The second thing that we learned is dark matter and dark matter interact very weakly, right? And the third thing, which is related, is the dark matter and gas also interact with very little. If dark matter and dark matter interact, then they will be like gases. They will be clustered in the middle instead of on the side. And of course, if dark matter and gas interact, then the gas will be able to stop dark matter, and you're going to get get into this situation as well, right? Yeah?
Are there another kind of interaction, like the weak interaction between, I don't know, dark matter and other kind of particles?
Yeah, so the question is, do dark matter have additional interactions with us, or like other particles? That's what we hope, and that's how we would be able to use some device in the lab to look for them. But a priori, like all we know is that they interact gravitationally, and they interact very weakly. And so this measurement tells us how weakly it interacts. So to give you some numbers, what people have found is that if I use sigma to tell you like the interaction cross-section between dark matter, right? So this is dimension length squared, over the dark matter mass. What this measurement tells us is that this is much smaller than, 1 centimeter squared over gram. Okay, so, and this is a very weak interaction between the dark matter. And many dark matter models failed at this step. For example, this tells you like electrons cannot be dark matter, or something that behaves like electrons cannot be dark matter because they would interact with each other too strongly. And we'll see how does this constraint change our view of a lot of dark matter models. Okay? So this is the first thing that we learned from bullet cluster, right? Good, bullet cluster? All right, okay. I need to fix this. Sorry, guys. So let's go to the second picture, which is evidence number 2. And that's the cosmic microwave background. So here I'm showing you a picture of COBE, which is a device that is 40, 50 years old. So it's a very old picture where we have a first global measurement of the cosmic microwave background. As you can see from this picture, like the resolution is quite bad. But simply from this picture, we learned a couple things. And the first thing is that there are these photons, which are called CMB photons. And the second thing is that on like large scales, it is relatively uniform, right? Like the temperature is roughly the same across the whole universe. And this temperature, which we call CMB, is equal to 2.3 Kelvin. And so the one other thing that we know about these CMB photons is that they are emitted at a time when the temperature of the universe was equal to roughly 1 eV. And that's when like the electrons and the protons will combine into an atom, and the photons will be emitted. and after which time the universe becomes transparent. Before, like if we have a lot of charged particles, then the universe is opaque. So this number tells us how much time it has passed since the time where like the CMB photons are generated and today. And what I will show you next is even at the time of the CMB, which is a very long time ago, because you can see like the temperature of the universe was almost 10 to the 4 times hotter than what we are today. So it was like a very, very long time ago. We already know that dark matter has existed at that time, which tells you some other properties of dark matter. Of course, to extract like a detailed information about dark matter, this is not good enough, right? This is very, very like non-precise. So in order to do better, we need a better picture. And so this is what we are doing now. So this is the CMB picture of taken by the Planck satellite. The different color codings here are a little bit hotter and a little bit colder than 2.73 Kelvin, the CMB temperature. So there are regions, of course, like it's not totally thermalized, like it's not like where like the temperature is not totally the same everywhere. There are fluctuations, and the exact point where like it is a little bit colder or hotter doesn't really tell you very much information. But like there are a lot of information which are stored in how these hot and cold spots are related to each other. So to study that, what we need are correlation functions. Okay. So how do we extract information from this picture? We need correlation functions. So what are correlation functions? So from this measurement, at each point, I can define a variable. Let me call it Xi. And the Xi variable at each point, let's say point X, is defined as the temperature at that point, X, minus this average temperature, right, over the average. So what this Xi tells you is how much this temperature is fluctuating at the different points. In the red points, like it is a little bit hotter, so Xi is a little bit positive. While at the blue points, like maybe it's a little bit colder, so the Xi is a little bit negative, right? So now, basically, I turn this picture of red and blue into a picture of Xi at different locations, right? As I said, each point, what the temperature is not very important. But the correlations are. And the correlation is basically, I'm asking if I see a point with a little bit hotter, like a Xi positive, what is the chance that at a different point y that I'm going to see Xi of a different value? Let's say let me use this. At this point, I find like Xi is 2 times 10 to the minus 5. At this point y, I get Xi is, let's say, like a minus 10 to the minus 5. So the question is, are these 2 points like correlated, right? So, and these are basically what is stored in these correlation functions. Okay. So what are the properties we have for these correlation functions from the CMB? Oops. So the first thing that you would think it has to be true is that all of these temperature fluctuations, because all of these temperature fluctuations are somewhat random fluctuations, so like this, whether like I choose this point to be x equal to 0, or if I choose this point to be x equal to 0, shouldn't change this correlation function, right? Or in other words, I can do a translation to both the x and the y variable, and I should get the same answer. And what it means is that this correlation function, okay, cannot be depending on like x and y independently. It can only depend on the difference between these two variables. Okay, so that's the translational invariance. How about like if I rotate? Like I can see it from this angle and I can rotate a little bit. Of course, I also like it shouldn't depend on whether I'm calling this the North Pole or like this point the North Pole, right? So meaning that I shouldn't really care about where like this vector x minus y is pointing, right? Does it pointing this way, it should be the same. So what it tells me is that not only it's independent of the exact location of x or y, it only depends on the difference, but it only depends on the absolute value or like the magnitude of this difference in distance. Okay, with me? All right, so of course, so this is what we know about the properties of this correlation function. It depends on one variable, and that's the distance between the 2 points. So I can take this thing, which is in position space, and turn into momentum space, where what I'm doing is basically a Fourier transform. I can express this function in terms of something that is in momentum space. And as you can see, like here, like what I have is a 2-dimensional figure, right? So all of these different correlation functions in this 2-dimensional space can be written with coordinates theta and phi, right? And these functions that I'm going to get is basically the spherical harmonic functions, y or m. And because I have rotational invariance, it shouldn't depend on m. So all of the information, well, or a lot of the information depends on this one scale L, right? So this a smaller L means large scale, and larger L, like a larger momentum, means a smaller scale on this picture. Oops. Okay, questions? So from where? From like L? Yeah. So okay, so like as we have here, where like the information is all stored in a correlation function, which only depends on the distance between 2 points. Now when I go to Fourier space, this information only depends on this L variable, which is basically something that tells you about the momentum of the mode of the oscillation. And these a larger L, meaning larger momentum, means smaller scales. And a smaller L, meaning smaller momentum, meaning larger scales. Okay? Yeah.
Do we know if there is any difference between dark matter in this early epoch or current dark matter?
We'll get to that. Yes. Good question. The answer is up to now, we don't know. We think there are not from all evidence we have collected, but they might be. So we'll need more experiments to know. Yeah.
Is it possible that there is any anisotropy in this?
Well, there are some anisotropy, but like these anisotropies, as far as we know, is all first Gaussian. And that's why like I'm only doing like two-point functions, correlation functions. And so far, like people have been talking about non-Gaussianities, but every measurement that we did, so far we have not seen non-Gaussianity. So we think that these temperature fluctuations are just random Gaussian, like a Gaussian random field or like a random Gaussian noise. Question? More? Okay. So that's what we did, right? Like we turn that picture and we go to this one. So this is basically the previous picture, but now like I'm expressing it in terms of the amplitude of the temperature fluctuation, or this Kc variable, as a function of L. And here what you are seeing are these acoustic peaks. Okay, so these are acoustic oscillations which show up as a couple of peaks in L space. Okay? So, the acoustic waves are some waves which are propagating in the baryon photon fluid. Okay? So does this remind you of something that you've seen, like in maybe a freshman or second year undergrad? No? Okay. What about this one?
The black body.
Huh? No, it's not a bad body, right? Like there are a lot of peaks. What about this one? Does it remind you of something?
The normal modes.
So I said like acoustic peaks, right? So what are acoustic waves? Huh? No, like a freshman year. Like I don't think you are learning very BAO in your freshman year, right? So these are acoustic waves, which are basically like oscillators, right? So if I look at this picture, it actually looks like this, okay? So, and the picture is basically like a damped oscillator. It's not a harmonic oscillator, it's a damped oscillator. So oscillator, right? If it is a harmonic oscillator, look like this, right? Okay? And if I have a damped oscillator, then the amplitude goes down. Oops. Now you see why I need to show you this picture. My drawing is not perfect. Okay? So, so what you are seeing is like an oscillator, right? Like which is decreasing in amplitude as it goes, right? So this still doesn't look like that, but let me say I don't want like the oscillation like of x and t of t, but I do the amplitude, right, as a function of time. Then what I get is that basically I'm flipping this part to absolute value. Then what I'm doing is I'm flipping this part to the plus, right? So now I have this, right? Okay? And that very much look like that, right? So basically, like without dark matter, you have the baryon photon fluid, and it's like the system basically behaves like a damped oscillator as the universe expands. And what you are seeing are, like in here, a bunch of basically oscillation peaks, which is decreasing as function of L, right? So this is basically what you see. And the amplitude is going to drop as like monochromatically, right? But so now let's, but this doesn't look exactly like what we have on the right, right? Their features are a little bit different. And the right is what we actually measured. So, and that is how we know that dark matter has to exist, okay? So to see that, let's go back to this picture, right? So let's say like now I tell you what my oscillator is. That's a pendulum, right? And I have a damped pendulum, meaning there are some friction as it is going around, right? It can be from gas or whatever. And now what I'm doing is, let's say like I put a mass here, which is attracting this pendulum, right? If I do that, then left and right are not the same anymore, right? And it will spend more time on the left, and it will go a little bit more to the left, while it will go a little bit less to the right, okay? So, this attraction is basically what is the dark matter is doing. So when we think about the baryon photon fluid, it is falling into the dark matter potential and then it's coming out of the dark matter potential, coming out of the gravitational potential. If I only have baryons and photons, then it is going into the potential and then coming out, right? So if I have dark matter, then the dark matter provides additional gravitational potential that this baryon photon fluid is coming in and coming out of. And the dark matter potential is staying in its place. So as a result, just like here, like if I put a gravitational body, I change the offset of the pendulum. In CMB, what I'm doing is basically, and like in this picture, what I'm doing is I'm changing where I call 0, right? Or where I call x equal to 0. So let's say like I move this point to here, then, sorry, maybe let me draw it again, right? Try to do my best. Let's say like 0 now is here, okay? So I'm flipping this part up, right? I'm flipping, well, this one like maybe I should have, well, let's say like I'm like this. So I have a little bit here, right? And I have a little bit here. So, so now what I'm getting is a curve which looks somewhat like this, okay? All right, and how much dark matter I put basically change where like I put 0 at. If I have dark matter, no dark matter, then it's symmetric. Now it's not, right? So, so this is basically the feature that is seen here. And then the main feature is that the amplitude of the odd peaks and the amplitude of the even peaks are different now. And the third peak in particular is higher than the second peak. And the reason is coming from the existence of dark matter and from this inverted peak structure. We know that dark matter has to exist. People happy with the harmonic oscillator? And also the picture? Okay, good. So that's evidence number 2 for dark matter, and that's the cosmic microwave background. So what do we learn from this picture? So I did the first time. You guys want to tell me what do we learn here? How about you talk to your neighbor and say what are the qualitative features we learn about dark matter? Do it. You can do English or like not, like I don't care. Just tell me when you stop, okay? And I can have a water.
Dark matter don't interact with the radiation.
Okay. So what's the result of your teamwork? What's number 1 thing that we learned? You want to say something?
I guess the dark matter relates oscillation, the concept, because the dark matter doesn't interact with the radiation. The oscillations relaxing, like an amortiguated oscillator.
Okay. Good. It doesn't interact with radiation or photons, right? Basically, mostly. Anything else? Was dark matter around at that point? Yes, right? Otherwise, it's not doing anything. So the second thing that we learned is dark matter existed when the universe is 1 EV or 0.1 EV temperature, right? And we know it exists in our galaxy today, but now we know like it has existed like a long time ago as well, right? And the third thing, which is a little bit more quantitative, is that we know how much dark matter is in the universe now, right? Because we know how much matter is in the universe, from this picture, what we can derive is the dark matter density is actually equal to the matter density, the baryon density, multiplied by a number which is 5, roughly. Okay? So it's kind of curious why like the dark matter density and the baryon density are so similar. But like it does is a little bit more than the amount of matter in our universe by roughly a factor of 5. And that, to get to this factor of 5 more precisely, You need to do a lot of work to extract information from this plot, but for all practical purposes, from this plot, you already know like the dark matter and the matter are comparable densities. Okay? That's what we learned from CMB.
I have a question
Yeah.
about this graph. How affect the relative behavior of the dark matter in the oscillations? What happens if the dark matter is like relativists, it's particles, it's very speed particles?
Yeah, so, right. So one thing I didn't say is like dark matter needs to be cold. And it has to be like non-relativistic things like even the BBN times.
How change when the dark matter is relativist?
Yeah, so I will tell you now. Okay? So now like you already know like the next item on this board. So the last thing that I will be telling you about are rotation curves. And this is actually the first time like we know dark matter existed, thanks to Vera Rubin and her collaborators. So what we are seeing from this plot is the rotation curve of a galaxy. If we only account for all the visible matter, meaning stars and gases, this will be what we predicted as the rotation curve inside the galaxy. Well, what we observed is something like this. Okay, and now like we can actually like extend to very, very far distances. The interpretation for this behavior is basically there are more matter than what we can see inside the galaxy, and that's what we the first time. Well, basically that's how like in the very early, well, almost like 90 years ago, Zwicky decided to call this additional component of matter inside our galaxy dark matter. Okay, so. The difference between these two curves tells you that dark matter existed. And as people have asked, like, can dark matter be relativistic? Well, it cannot, because if it is relativistic, then it will escape the galaxy. Right? If it is moving at a speed which is faster than the escape velocity of the galaxy, then it will escape, and it will be like a uniform on large scales. And it doesn't, like it follows basically like a profile of rho of r, like the density of the dark matter as a function of radius from the center of the galaxy, which agrees with a collisionless cold dark matter particle. And that's how we know that dark matter has to be cold today, and how we know like these particles exist in our galaxy. So the reason I want to put like a rotation curve at the end is because now we are doing much, much better. And the reason is this new instrument called the Gaia Telescope. Do people know about Gaia? Oh, good. Some people actually know about Gaia. Great. So Gaia is a new like a mission where basically like all it does is measure the location and the velocity of stars. All the stars that we can see inside our galaxy. So, and also in large and small Magellan Cloud. So the amount of stars that this mission is seeing is order 10 to the 9. And we are measuring their velocities and positions to really, really high precision. So on this plot, each of these lines, curves, are basically a star trajectory that we see inside our galaxy. So as you can see that these curves are very, very finely detailed, much more than the rotation curve I showed you from the last slides. And what it means is now that we have a much, much higher resolution picture of the dark matter density distribution in our galaxy. So what the Gaia gives us is a measurement of two things. So here, the first thing it gives us is a measurement of the dark matter density as a function of r, because that's how we see the stars are moving. And the second thing is it tells us about another function, which is basically how clustered these dark matters are. Right? So if I have a lot of dark matter clustered into a small blob, and let's say like I have a blob here, and I have some star here, right? And if I have a very, very dense blob, then like this dense blob is going to affect the star motion around it. And given that we don't see stars which are affected by some blobs of dark matter somewhere, it tells us that we do not have a large, heavy, like a very, very dense blobs of dark matter, and it places constraint on dark matter distribution in our galaxy. So, so these are the two things that the Gaia measures, and it tells us that first, as we already said, dark matter is non-relativistic. Inside the galaxy, and secondly, dark matter is, does not dissipate very much. Okay? So, so this second thing is basically what I was saying earlier, right? So if it dissipates a lot, like the stellar model forms stars, form neutron stars, form all kinds of stellar objects, well, like even solar systems, and things like us. And it does seem like the dark matter doesn't want to do that. And as a result, we know that it doesn't want to dissipate very much. Okay? Okay, so from all this evidence, what we arrive at is the thing here. It's something that you can buy when you go to MIT, which is a ridiculous, what's it called? Like way to sell knowledge. The fact that it works like is a scam for all financial purposes, but it does tell you a little bit about what we know about dark matter. So dark matter is here. It's everywhere, and you can get a box, and you roughly know how much mass in dark matter that is in this box, right? And that's what they are selling. They say like there is this much gram of dark matter inside the box. It has a density which is comparable to the baryon density, and it also tells you what roughly the amount of density it has compared to other densities that we know, right? For example, the dark matter is like within this box is 10 to the minus 27 gram, while things like air is roughly 1 gram, okay, inside the box. And this gives you a sense of how little dark matter that we have in our local environment. We have a lot more dark matter in the whole universe compared to visible matter. Well, not a lot more, but like a factor of 5 more at least. But inside this box, which is around us, the amount of dark matter is 27 order of magnitude smaller than what we have as gas, right? So, so that gives you a sense of how hard it would be to look for this component of matter on Earth because it is such tiny densities. Okay? You guys are welcome to come up with other ways to make money. Might be good. Yeah, okay. All right. Okay. Okay, so let me summarize a little bit what we learned today. So there are a couple things that we learned. The first thing we learned are these qualitative features that we extracted from these plots that we see, right? So a few things that is a little bit more qualitative can be deduced from these statements. So the first statement that can be deduced is that is combining this statement with something that I didn't write down, but like basically like dark matter exists in the galaxies, right? So when I combine the fact that dark matter was around very early on, and it is around today in our galaxies, what we get is the decay rate of dark matter has to be really, really tiny, right? Okay, so it won't even be able to decay within the age of the universe, which is a very, very long time. So this tells me a couple things about what type of particles can be dark matter, right? So I'm not sure if you have seen a Feynman diagram. This you can think of it as a Feynman diagram, but like it doesn't really matter. All I'm saying is dark matter can potentially, let's say, like decay to 2 photons, right? And the only important thing is that for such a process, the rate is proportional to the coupling square times the mass of the particle to start with. Okay? So you can take, if you know Feynman diagrams, then you can derive this equation, but like if you don't, the mass of dark matter is the only energy scale in the problem, so this is what it has to be, right? So we know that gamma dark matter is very, very tiny, so it tells you basically either G is really, really tiny, or M is really, really tiny, right? Simple. In principle, like it actually, it tells you both. It tells you like both of them has to be really, really tiny. And if that's the case, then what we have are axion dark matter. Axion is a particle which interacts really, really weakly, and it is very, very light. So, and that's the reason why it didn't decay, right? So that's type 1. What is some other type of particle which won't decay? Does the electron decay? Why doesn't electron decay? Huh? Anyone? It's charged, okay? So it is charged under something, some symmetry which is conserved, right? You cannot create like a electric charge, and also you cannot create things like a baryon number, which is why like the proton is stable, right? So the second way, like I can have a dark matter which doesn't decay, is by symmetry, right? So if I have a conserved number, a quantum number, let's say like a baryon number, or in this case, let's call a dark matter number, or in more precisely, like let's say like I have a U1 dark matter number, which is conserved, then dark matter won't be able to decay, right? So this idea of using a symmetry to make sure that dark matter doesn't decay is basically the idea behind WIMP. And of course, like for WIMPs, the symmetry that is protecting it is a little bit more complicated. It's a combination of supersymmetry and R symmetry. But doesn't matter. There is a symmetry which makes sure that my particle doesn't decay. Okay, so that's WIMP. So there is a second thing that we learned that is summarizing all of these things together, and especially we are going to use this formula, is that dark matter doesn't interact with each other very much. And the interaction, in terms of Feynman diagram, is something like this, where, but like it doesn't really matter. Time goes this way. I have some particle coming in, and they interact. Let me just draw it a blob, right? And some particles coming out. So what we know is that this cross-section, interaction cross-section between dark matter is very, very small. And this cross-section can be written as some coupling constant to the 4 over m squared, okay, where the mass of the dark matter is squared. Okay, so the fact that sigma is small, right, tells me that either I have to have some particle which is coupling very weakly, or if the coupling is order 1, then this particle has to be somewhat heavy. Okay, so so the case where like I'm protecting the dark matter from a symmetry, I can have like some large-ish coupling, then like these particles have to be heavy. Tomorrow we'll see how heavy they are, and the energy scale that we're going to get to is roughly a TeV. So the second possibility is, of course, like when G is very small, it's where like what happens to axions. G is very, very small, as we know, and those particles also they interact. So So now we got to the point where we can draw one of the most famous plots. Where's the? Here. That you will see when people talk about dark matter, and that is the mass range dark matter can be. Okay, so draw axes, maybe two of them. So here is basically axis which shows you the mass of the particle from very light to very heavy to crazily heavy. Okay, so on the left-hand side is where like what dark matter mass can be when it is the lightest. And this number, due to one of our colleagues' recency, has been, it was like 10 to the minus 22 if you asked me like 2 years ago. Now the number is 10 to the minus 3 times 10 to the minus 19, which is how light this particle can be, right? So one exercise you should try to do is convert this into length units, right? You can compute what's the wavelength of this particle, or the Bohr wavelength of this particle, 1 over mv. And what you will find is that this is an enormous length. It is a length that is order parsec to kiloparsec, right? So kiloparsec and parsec, if you remember Ricardo's lecture, is what the size of the galaxies are. Okay, so basically what you have at this end is that the particle wavelength is so big, at some point it doesn't fit into a galaxy anymore, right? The Bohr wavelength of this very, very light particle is so large that, that I cannot really fit it into the galaxy. Of course, it's not a viable dark matter candidate. Okay, so that's where like this mass comes in. I can make it heavier and heavier, and around like EV or 10 EV, we hit a special point, and that's the point when before this point, the way that we view these dark matter particles are more like waves, right? So as I said, like the particle is the size of the galaxy. Of course, like each particle is very, very little energy density. In order to have like a large enough energy density in dark matter, I really need like a ginormous amount of particles fitting in the same galaxy, and they are all in the same state, roughly. And the way to describe those things are waves, and in particular like lasers, photons, right? That's how we talk about these large particles with a huge amount of occupation number, right? So in this range, we mostly talk about waves, and all the detector technology I'll be telling you at the end will be about how we look for waves, and a lot of them will come from how we look for photons. So the picture changed around the time when the mass is order eV. At this point, what happens is that the density of dark matter inside the galaxy is comparable to mass to the 4. If you want to be ultra careful, like it's also multiplied by the dark matter velocity in our galaxy, which is 10 to the minus 3 cubed. Okay? So at this point, basically the occupation number within the Bohr wavelength becomes order 1. Okay? So above this point, roughly we should be more like when the mass continues to increase, at some point we should be thinking of them as individual particles. The wave functions are not overlapping anymore, and we are thinking about individual particles hitting your detector. And that's where the WIMPs are. Okay, so WIMP is here, and axion, most of them is in the regime of waves. So a WIMP, as we'll show you next lecture, has a mass that is order TeV. So it is at a point where like basically it's very, very tiny compared to its the separation between two particles. And we'll be basically talking about particles scattering with the detector instead of waves. Okay? So the particle description of a dark matter ends when the mass is on order n Planck. Right? We cannot really talk about particles or like individual particles with mass that is much heavier than Planck. But in principle, like we can go above that, right? We are all like much heavier than one Planck, right? Planck mass, if we put it in gram units, is very, very tiny. So if dark matter can form structures, right, like a molecule or like a human, right, we are all heavier than Planck. So if a dark matter can form structures like us, then in principle it can go above this axis. And the time where it will actually stop is when the mass becomes order the mass of the sun. When you go much above that, then the mass, basically like each dark matter particle is too granular inside the galaxy. And when we measure like these rotation curves with Gaia, you will be able to see that there should be some additional granular structure, and the things won't be like a very uniform anymore. So anywhere between like the Planck mass and maybe like even 30 or 40 solar masses, we can have composite dark matter, right? Like composite particles like things like us, and for which like there are no, actually like very little theoretical description for. And generally we think like it's very hard to get these particles as dark matter. And that's the question. We'll start next lecture, I think. I'm roughly on time?
Yeah, perfect.
Okay, so, so good. All right, so two more things before I totally stop. The first thing is that from next lecture, I will be telling you about how we evaluate a specific dark matter candidate and how we can write down like a model and track its thermal evolution in the early universe. We'll first do it for WIMPs, and then we will do it for axions. So in order to do that, it will be good if you take a look at something that I put in the reading material, which is known as the FRW universe, the Friedman-Robinson-Walker metric, and the universe evolution with this metric in a radiation-dominated universe. So, so from next lecture, I will be telling you how the dark matter particle fits in this framework. And actually, like, how many of you have heard about this already? Like, know what is FRW universe? Okay. So your task, whoever raised hand, is to teach the people who didn't. Okay? And if someone like didn't understand next time, it's your fault. All right. Okay. So that's all I want to say for this lecture. Thank you. Questions?
So you told us that depending on the mass range of the dark matter, it makes sense to think it as a wave. But and then I think you, correct me if I'm wrong, you told us that okay, so how can we look for waves, so photons, but it is dark, so maybe we should look for another kind of wave. And I was thinking, oh, do you think that maybe gravitational waves experiments could be a good idea to look for dark matter candidates? Good,
very good question. Yes. So first, the answer to both is yes. So dark matter behaves like waves. So there are actually like two main ways that we'll be talking about how we look for this dark matter. And one idea is how can I turn a dark matter wave into a photon, like with some like a structure, okay, condensed matter usually, to turn the dark matter into a photon and look for the photon. And the other way is to use a detector which couples to the dark matter wave directly. And for example, LIGO is one of these detectors we can use to look for dark matter waves. And there are very strong constraints that is placed on using these resonant bar detectors, like resonant bar detectors, and also like LIGO detectors. And yeah, that's the right track. Like that's how we are looking for those things. Yeah, exactly.
I don't know if in the scale of these masses, but I know about the proposal of dark matter being primordial black holes.
Yes.
What about that? I mean, where does it fit, or?
So, yeah, good question too. Like, so this is roughly like the primordial black hole is one type of like this composite dark matter. We cannot really write it as a particle, like, but they fit in a range which is roughly like this. And for most of the parameter space, it cannot be 100% of dark matter. There's a small range where it can still be 100% of the dark matter. But like so far, like I don't think like people know of a good way to produce it in the early universe with the distribution that we want.
How accepted is this proposal in the scientific community?
PBHs, I think like a lot of people are looking for primordial black holes, and well, people look for it like regardless. But like to me, like it's not the most well-motivated dark matter candidate because of its lack of production mechanism. Actually, like next lecture, I will start with 4 questions that you can use to evaluate any dark matter candidate you want to evaluate, and you tell me like what type of dark matter is better or worse. And yeah, but like yes, like PBHs is actually like the leading candidate for like some like composite dark matter, and there are a lot of like work done to look for it.
Okay, thank you.
More question? Yeah.
So recently, I have read some scientists saying that dark matter may be an anomaly of gravity, and maybe like I think they call it monde.
Yes. Yes.
And given all the evidence you showed us, I mean, the first thing we think is, oh, it must be a particle. So why is there people that think it must be a modified, an anomaly of gravity?
Right. Okay. So monde is a very, very old theory, and it is developed during the time that we know a little bit about rotation curves. So there are 2 ways to explain the rotation curves. One way is there's more matter. The second way is there's more gravity, right? So if the gravity becomes stronger at some point, then that would like also explain like what happens to rotation curves. But I think like monde, as far as I'm concerned, is a dead theory because of bullet cluster. And that's where like I started with this. And the reason is that here we clearly see the separation of where like the gas are, which is mainly like the main component of gravitating normal matter, and where the gravitational potential is. So from this picture, you will not be able to write a monde theory, which somehow tells you that the gravitating potential is coming from like the blue regions instead of the red region where the most of the gravitating normal matter is. And because of this picture, I think like I don't think any monde theory like even try to explain this. So I don't think like yeah, now like it's not a viable possibility anymore.
You know how to discuss with someone that says, "Oh no, monde is clearly."
Yeah, just show them this picture and ask them to explain. Right. Well, with CMB too, like it's pretty much impossible to change gravity. Yeah.
So dark matter interacts only gravitationally with other type of particles, right?
So far, that's the only interaction we know.
Yeah. So it couldn't be able that for dark matter, inertial mass and gravitational mass could be different, or this is something already proved wrong?
Well, there are many ways to to think about this question. So so normally when we say if the inertial mass and the gravitating mass is not the same, we call it equivalence principle violation. Right? So the equivalence principle tells you everything with the energy gravitates the same. Right? So there are measurements done for equivalence principle violation about dark matter. And so the way that people do it is by seeing how, if I have two galaxies and they are rotating around each other, you can see how the galaxy and the dark matter part of the galaxy and the matter part of the galaxy is falling into the gravitational potential of the other one, right? So if there is equivalence principle violation in the dark sector, then what happens is the matter part of the galaxy and the dark matter part of the galaxy is going to separate. And especially it's going to, for disk galaxies like the Milky Way, it will cause the disk to bend. And we didn't see this effect. So we think I think roughly now the constraint on how much equivalence principle violation dark matter can be is less than 10⁻³ of the gravitational strength.
Okay, thank you.
I think it might be stronger, but I don't remember exact numbers. So in my units, I'm always right. Okay.
More questions?
So you said that Mond was out of the way, but what if you can join the theories together and dark matter is governed by some other theory on gravity?
What if, so the question is, what if dark matter is governed by some other theory of gravity?
Other interaction, other...
Yeah, so that's actually the same question as the previous one, if it has some additional interaction, right? Their interaction is not purely gravitational, on large scales. And if we assume the only interaction is gravity, then that shows up as an equivalence principle violation, meaning different species of particles is falling different way, right? Interacting different way. And so the same equivalence principle bound will tell you that the gravitational effect of the dark matter is exactly the same as matter. Okay? I think there's one more.
Yeah, my question was, if dark matter behaves like waves, does this mean that they have some bosonic statistics, or
yeah,
is it
so
independent?
right. So that's a very good question, and I forgot to mention it, actually, so thank you. For any mass that is actually lighter than keV also, the dark matter particle can only be a boson. It will have both statistics, and the reason for that is if you have fermions, right, you cannot have a lot of them occupying the same state. That's Pauli Crucian principle. And from that, you'll be able to see that if the particle is lighter than a keV, the Fermi momentum of this particle, if it is a fermion, the Fermi momentum of the particle is going to be too large, and the Fermi velocity is going to be too large that it cannot be cold. So, and the criteria you can show is basically you can compute VF for the, assuming it is a fermion, let's say a 1 keV fermion, we can compute the VF for this particle, and it's roughly around that point that the VF becomes larger than dark matter velocity, which is 10⁻³. So anything below a keV, it has to be a boson. Anything above a keV, there's no overlapping, right? So whether I treat it as a boson, a fermion, or just a Boltzmann statistic, it doesn't really matter anymore. Because it's relativistic also. You are doing a non-relativistic, because it's non-relativistic, and you are doing a non-relativistic expansion, So yeah, like you are doing shorting equations, as Pedro was doing. So at that point, like there's no difference. Yeah.
I have a small question. So you mentioned this first number, this 10 to the minus 9. You said 19. You said you could estimate it by the size of the galaxy, but you also said it changed by 3 orders of magnitude recently.
Yeah, because different galaxies are different size. So right now, so this is actually done by like Neil Dalal, who's our colleague. So he examined these ultra faint dwarf galaxies and how stars really the star dynamics in these galaxies. So in the last lecture, I will tell you about Brownian motion, but people should maybe know a little bit about Brownian motion, right? So what happens is like the stars are basically like the pollen, while the dark matter is like waves of in the underlying fluid. And if you have like a particle which is too light, then they will actually like kick these stars around, and the star will want to evaporate from the galaxy center, or like the center of this ultra faint dwarf, and symbolize and becomes bigger. Like it will go out like a random walk if this mass is too tiny. And the fact that we don't see that means that the mass of the dark matter has to be bigger than the star. Yeah. The limit from our galaxy is roughly 10 to the minus 22 because the Milky Way is actually something big. But like there are a lot of more small ones which we have also more precise measurement and cleaner. Yeah.
How changed the relation between the baryonic matter and dark matter in the universe histories, and in which interactions can we constrain these relations?
Okay, so the question is like we know from the CMB it's a factor of 5. Like as a universe evolve, like does this ratio change? We measure. So the first thing that we measure is the CMB, right? At that time we know the ratio. And at a later time, there's I don't know how much cosmology you know, but like as the universe cools down and the perturbations start to grow, like the small perturbation that we see on the CMB map start to grow, you eventually goes through like what is known as the structure formation. Basically, like the matters and dark matter cluster into clumps, and galaxies form. So we also have measurement of galaxies and their statistics and their the correlation of their fluctuations, and that field is called the large-scale structure. And from those measurements, we also know like roughly what's the ratio between the matter and dark matter density. And at that time, like we also can get a similar precise number on this ratio. So basically, like from the time of the CMB all the way to today, we are pretty sure that this ratio changed by less than, I would say, like a percent or a couple percent. Yeah.
Regular matter in higher energy scales, we have some couplings and decouplings of the interactions. Could perhaps dark matter in some energy scale couple with another interaction like the weak force, or?
It can couple with another interaction. So are you saying like dark matter can couple to us, or?
Yeah, interact with light perhaps in a given energy scale.
Well, like, so we'll be talking about dark matter interactions from next time, but like, it's usually like what we think is so for WIMPs, what we think is they interact with some high dimensional operator. So like it's, we are having some operator of the dark matter, right, and the operator of the standard model over some energy scale. So this is like the Fermi interaction, right, between electrons and nucleons, right? Like the weak interaction. So and then like the scale is you can think of it as the scale of the new mediator between the force between dark matter and us. So yeah, like it will usually tell you about the energy scale in this case, because like it is interacting. It's a short range interaction mediated by a very heavy particle. But like at the same time, it can also be like some interaction which is mediated by a massless particle. Just like the company has to be very tiny. Those interactions are usually taught. People usually say like these interactions are mediated by something called a dark photon, which is basically like our photon, but has a tiny mass. I don't know if this answers your question, but this is roughly like the picture. We'll be doing this case next time. More? Good.
Let's thank Junwu.
Thank you.
So you have plenty of problems to solve on the website, and as Nathan said, in the first floor there are plenty of tables. There's a big empty room there, so you can. Some of you can stay here. Some you can also go downstairs, check which place you like the most.